In example 4, we will do something interesting. We will model the evolution of current in an electric circuit with time. So let me describe this electric circuit to you. We have four objects in this circuit, all connected sequentially. They are a battery that creates constant voltage of 60 volts. We have a resistance of 12 ohms, and we have an inductance of 4 Henry. And in addition to that, we have a switch. So at the beginning, at the moment of time t equals 0, there is no current. The switch is turned off. So to show that, we're going to say that the current at time 0 is equal to 0. Now, at t equals 0, we will turn the switch on. The current starts flowing in this circuit instantaneously, and the question we would like to answer is, how will this current evolve with time? Assuming, obviously, that at the beginning there was no current. Great. So what we will do is we will think about 2 points on this circuit and think about the voltage drop between these 2 points. So we have resistance. There is a current flowing through it. So by Ohm's law, the voltage drop between these 2 points must be the resistance times current on the one hand, and on the other hand, it consists of the voltage created by the battery here. So the voltage of the battery is constant, even though we may think of it as function of time. So this understands that up to the moment t equals 0, E of t was 0 as well, and then it jumped abruptly to 60 volts at t equals 0. And so this same voltage drop, on the other hand, is given by the voltage of the battery plus the inductance. Now the inductance, according to the Faraday's law, comes with a minus sign. So I have minus L, and times L is multiplied, the coefficient of inductance is multiplied with the rate of change of current in this coil. And so I have rate of change of current in the coil, like so. So the minus sign here shows that the inductance tries to counter the change of current in it. So this term comes from the Faraday's law. And what it is saying, the minus sign is saying that if your current is increasing, the inductance acts as some additional voltage that tries to prevent this increase. Conversely, if the current in the circuit is decreasing, inductance will act as additional voltage that tries to prevent this decrease. So basically, when the current is increasing, as we're going to expect now, once we turn the switch on, first there was no current, but now there will be some current. And so the current is going to be increasing, and so inductance at this stage will act as some additional voltage counteracting what we have here. In other words, what this is saying is that this term here is going to be negative, so minus the positive quantity. Now let's go ahead and substitute the quantities we have here in this equation that we know values for. So we have 12 ohms times the current gives 60 volts minus 4 Henry times the rate of the change of current, which I write as the derivative of I. All right, so this is a differential equation. I have the unknown function. I don't need this bold sign here. So I have the unknown function, and it is related in this way to its derivative. So what I want to do first is I'll get rid of this factor of 4. So I'll divide both sides by 4. So this gives me that 3i equals 15 minus di over dt. Let me go ahead and express di over dt as a function. So I want to put di over dt in the left-hand side, everything else at the right-hand side. So this gives me that di over dt, the rate of change of the current in this circuit, is given by 15 minus 3i, which is 3 times 5 minus I. All right, so this is an equation where I is the unknown function. The right-hand side, I claim, is again a separable differential equation because the right-hand side can be expressed as a product of two factors, one of which depends only on I and not on t, and the other only depends on t. Now here, incidentally, the factor that only depends on t is actually a constant, so it doesn't even depend on t, strictly speaking. But that is okay. We are okay with functions that are constant as long as it is independent of I. So let's go ahead and separate the variables. We'll have di over 5 minus I in the left-hand side. We're putting all the terms that contain I in them. And in the right-hand side, I'll have 3 times dt. And then let me go ahead and integrate both sides of this equality. I'll have minus logarithm of 5 minus I equals 3t plus a constant. Now I want you to think about this minus sign here. Where does it come from? So it comes from the minus sign in front of I. If I just go ahead and differentiate this expression here, I'll get 1 over 5 minus I, but then the minus will give me a factor of minus 1 because of the chain rule. So I want to compensate for that. That's why I'm putting a minus up front here. And so the goal now is to solve this equation for I. What we will do is we will apply the same procedure that we applied in the previous equation, in example 3, where we raised e to the both sides of inequality. Except that here, what I want to do first is I'll multiply both sides by both sides of this equation by minus 1. I will also change this constant into c1. And so I have logarithm of 5 minus I equals minus 3t plus c. So notice I have changed c1 to minus c. So this here is same as minus c1. All right. So next I'm going to raise both sides, or raise e to the equation in both sides of this quantity here. I have e to the log of 5 minus I, absolute value, equals minus 3t plus a constant. Oops, that should be in the exponent. All right. Now, in the left-hand side, I just have logarithm of the. I'll just have the absolute value rather, because e and the exponentiation and natural logarithm cancel each other. So I have 5 minus I on the left-hand side equals, now in the right-hand side, I'm going to do the same thing. I will write this product as e to the c times e to the minus 3t. Now e to the c, for c taking any fixed value, is some constant which happens to be positive because the exponential function is always strictly positive. Now I have k times e to the minus 3t in the right hand side, where k is not allowed to be negative again. Now what I'm going to do with that is I will observe the plus minus that is going to come from opening up the absolute value, like so. I see that if absolute value is equal to this thing in the right hand side, then 5 minus I is plus minus of this expression here, where I'm again having to assume that k is strictly positive. Now this means that 5 minus I is k times e to the minus 3t for any k that is not 0. And finally, I can write this as I equals 5 minus k times e to the minus 3t. Now, the final question that remains to be answered is whether k can be 0 and what is its value if we take into account the initial condition. So if we plug in k equals 0 in here, we see that I must be constantly 5. So for the constant, for I equal to the constant 5, we have its derivative being 0, and in the right hand side we have 15 minus 3 times 5, which is also 0. So indeed for I equal to 5 constantly, we have yet another solution. So here k can in fact be any real value. Great. So this is the general family of solutions of this differential equation. Now let us go ahead and determine the solution that corresponds to our initial condition. So here was our initial condition. It meant that at the beginning, at t equals 0, there was no current in this circuit. We're going to use that. So I of 0, it must be 0 on the one hand because of the initial condition, and on the other hand, it must be 5 minus k times e to the minus 0, that is to 0. And so this here is 5 minus k. And this allows us to conclude that k must be 5, and then our solution, the solution to our problem with initial condition, has to look like so. So this is I as a function of t, and it is given by 5 minus 5 e to the minus 3t. So this is the answer to this differential equation with initial condition. Now let's think about what this tells us about how this electric circuit evolves. Right? So if you think about the function that we have here, it behaves like so. So it starts, so first of all, it is indeed 0 at 0 because that was the initial condition. Secondly, when t goes to infinity, what happens when t goes to infinity? What happens when you turn on the switch and then wait for a for a very long time? Right? So in this case, you are looking at the limit when t goes to infinity, I of t, that is the limit of this expression. Right? Now, what is the limit of this difference? Well, the limit of 5 is going to be 5 itself, and limit of the second term when t goes to plus infinity is 5 times something that goes to 0, in fact. So if you think about what happens to e to the minus 3t, so e to the minus 3t has its graph looking something like this. And as a result, when t goes to infinity, e to the minus 3t goes to 0. And so in the limit, we get that I of t converges to 5. Okay, so that means we have a horizontal asymptotic at 5, like so. This is the horizontal asymptotic of our function. So this is I of t as a function of time. And then what our I of t does, it converges to 5 as t goes to infinity. In fact, it converges to this asymptote very, very quickly. So after a very short time, the current will be stabilized at 5 amperes. Now, that makes sense because it means that once you turn on the circuit, the current very quickly will level out. At the same time, it makes sense because the value that we get here, 5 amperes, is what you would obtain if you divided the voltage by the resistance. So it's as if limiting current, right, this the limit of I of t when t goes to infinity, it behaves as if it were a pure Ohm's law, as if there was no inductance in this circuit. So basically what this says is when you turn on the circuit and wait for sufficiently long time, then inductance has no impact on the value of the current. The current stabilizes at the same value as it would have if there were no inductance at all. And this makes sense because inductance has impact on your circuit only when current is changing because of the way Faraday's law looks like. And so this is how you model a simple electric circuit using differential equations.